This lecture will focus on the introduction of Lewis acids and bases. We've talked in the past about Arrhenius acids and bases and Bronsted-Lowry acids and bases. Lewis acids and bases is the most broad and the most recent, so the most all-encompassing. So every Bronsted-Lowry acid or base, as well as every Arrhenius acid or base, is also a Lewis acid or base, but not vice versa. The basic definition is that a Lewis base is an electron pair donor. Now remember, when we were talking about Bronsted-Lowry acid bases, we talked in terms of proton or hydrogen ion donor and acceptor. So the key difference is a Lewis base, as I said, is an electron pair donor, and a Lewis acid is an electron pair acceptor. So we'll talk about what types of compounds fit either one of those definitions and what type of products you can get. We're going to be getting into the mechanism of acid-base reactions. That is, we know that valence electrons are what are used to make new bonds, but how exactly does that happen? And so we're going to just skim the surface of how valence electrons move around on different atoms to break existing bonds or make new bonds. So I'm going to start by talking about intermolecular forces, which we've gone over. So if I asked you to draw the Lewis dot structure for acetic acid, and as well as water, and then show the most important or the strongest intermolecular force between those two. And by the way, acetic acid is the acid that's in vinegar, if you didn't know that. I think it's like 5% acetic acid in water. But anyway, so let's show that. Both of these, water and acetic acid, are capable of hydrogen bonding. Let's go ahead and put our partial charges where they go. Anytime you're going to show intermolecular forces, it's good to have the partial charges because then that kind of directs you in how to set up the intermolecular attractions. So as a reminder, the more electronegative atoms have a partial negative charge, and then the less electronegative atoms have a partial positive. So I think we all know that opposite charges attract. So this hydrogen, which is attached, bonded to an electronegative oxygen, will be attracted through intermolecular forces to an oxygen on water or an oxygen on another acetic acid molecule, either one. And let's see, we could do another one up here. Okay, so we could show this electropositive hydrogen on water sharing an intermolecular attraction with the oxygen on acetic acid. So basically any oxygen or any hydrogen that is attached, that's capable of hydrogen bonding. So remember, that's hydrogen's bonded to either a fluorine, oxygen, or nitrogen. Those are the three types of hydrogens that are capable of hydrogen bonding, and those are three of the more acidic hydrogens, and that's just not a coincidence. There's a reason for that. So let's look at a little bit neater drawing of the intermolecular forces, the hydrogen bonding forces between these two molecules. And as you can imagine, if you have a strong pull between these two, you weaken the bond between the hydrogen and whatever electronegative atom it's bonded to, which remember would be either fluorine, oxygen, or nitrogen. So this bond gets weaker. It's kind of ready to break. And so given enough energy, it actually will break. What do you get when it breaks? Okay, so if we take this hydrogen ion and move it onto the water molecule, we're left with the anion of the acetic acid, which we call acetate, and then a water molecule with an extra hydrogen ion, which we call the hydronium ion. Okay, so hydrogen bonding is it's one real important mechanism that leads to an acid-base reaction. And even though these can be classified as Lewis acid bases, it's probably easier to wrap your brain around thinking of the Bronsted-Lowry definitions. All right, so let's compare. Arrhenius definition is just so long ago, I'm not even going to include that in the comparison here. So a Bronsted-Lowry acid is a proton, which is a hydrogen atom donor. Now let's look at a Lewis acid. A Lewis acid is an electron pair acceptor. Okay, so it was a donor of a proton, it's an acceptor of electrons. That makes sense, okay, if you think about it. If you're giving away a hydrogen ion, you're leaving behind an electron pair. So it's kind of saying the same thing almost. So Bronsted-Lowry base is a proton acceptor. A Lewis base is an electron pair donor. Okay, so if you think of a typical Bronsted-Lowry base, okay, so let's just say we know that water can act as an acid or base depending on what it's in the presence of, but let's pretend like water's our base here. So as a base, it's going to accept, as a Bronsted-Lowry base, it's going to accept a proton to become the hydronium ion. Okay, but by doing so, it has also donated an electron pair. So let's look at that. What has happened is this electron, one of the lone pairs, one of the electron pairs on the oxygen, has been donated to make a covalent bond with this hydrogen ion. Okay, so you can look at it both ways. Okay, this water molecule is a hydrogen ion acceptor, and it's also an electron pair donator. Now we're going to start, I told you we're going to talk about the mechanism of acid-base reactions, and we're going to demonstrate that using these curved arrows that you see, that you see right here. Okay, so those curved arrows are used to show electron flow. Okay, and they start from the electron source. Okay, they start from the electron-rich site, and so that's typically a lone pair of electrons, electron-rich site, and they point to the electron-deficient atom that's usually, or site that's being attacked. So they point, the arrow points to electron-deficient site. And another thing I want to point out is the vast majority of the time, these curved arrows show you exactly where new bonds are being made or old bonds are being broken. So I would like you to think for a minute and tell me how you would classify the following two compounds as far as acid-base goes. So consider Bronsted-Lowry acid or base as well as Lewis acid or base, and put the video on pause and see what you come up with yourself. They could be both, or they might only be one, or they could be neither. So give it a shot, and then I will go over them with you. So let's look at the hydronium ion, and let's think of the definition, right? So a Bronsted-Lowry, first of all, I think this would be an acid because it's got a bunch of hydrogens attached to an electronegative atom. So Bronsted-Lowry acid is a proton donor. So if that donated a proton, what would be formed? We would just get water. That seems very reasonable, right? Yeah. So I would say, okay, That can be a Bronsted-Lowry acid, sure. Can it be a Lewis acid? Well, I don't know if you remember me saying in the beginning of the lecture, but any Bronsted-Lowry acid or base is also automatically a Lewis acid base because the Lewis acid base is the most broad definition. So yeah, it can also be a Lewis acid. Okay, so I would say the first one can be both. Let's look at the second one. Let's see, there are no hydrogens to donate, so it cannot be any type of acid. Well, it can't be a Bronsted-Lowry acid because there are no hydrogens. Okay, so Bronsted-Lowry acid is out. Okay, no hydrogens. All right, so could it be a Lewis acid? What's the definition of a Lewis acid? It's something that can accept an electron pair. What would want to accept an electron pair? Something that was electron deficient. How would I know something's electron deficient? Well, cations are electron deficient. Something with a partial positive charge is electron deficient. Or something with an incomplete octet is electron deficient. Does this BF3 meet any of those? Yes, it turns out that boron is a moron. That's how I used to remember it. Boron is happy with only 6 valence electrons around it. 2, 4, 6. Turns out that boron has an empty orbital, and so it can be an electron pair acceptor. And so this one, BF3, is only a Lewis acid. Okay, it can't be Bronsted-Lowry because there are no hydrogen ions that can be donated. All right, so this might show it a little neater than what I did. So again, because boron trifluoride only has 6 valence electrons and everything likes to have 8, if something electron-rich comes around with a lone pair of electrons to donate, that's what will happen. Okay, so in this case, this arrow, remember, starts at the electron-rich, the electron donor, and points to where the new bond is being made, or the electron-deficient atom. So now you see here, we have an extra fluorine atom. I'd also like to point out conservation of charge here. It's not shown very clear, but this is the fluoride anion with a -1 charge. So whatever overall charge you have on the reactant side of any reaction, in this case it's -1, you must have that same charge on the product side. So don't forget to put a minus for this product so that you have the same negative charge on both sides. Okay, now let's look at NH3. All right, so we didn't have NH3 on the last page. I must have changed what I did, but oh well. So how would you classify NH3? Well, it has hydrogen atoms, and they're attached to an electronegative element, nitrogen. So could that act as an acid? So acids donate, they give away hydrogen ions. So if that gave one away, we would have this left. I guess that's possible. But what's a lot more probable, and you'll understand why by the end of this PowerPoint, hopefully, is that this can behave like a Bronsted-Lowry base. In other words, a hydrogen ion acceptor. It has a nice lone pair of electrons that can form a bond with a hydrogen ion. And this is called, let's see, the beginning is ammonia molecule. And this is the ammonium ion. And it turns out that nitrogen with an extra bond and a positive charge is more stable than nitrogen with a negative charge. So again, we'll discuss that later. So you can classify this as a Bronsted-Lowry base. As a stretch, you could classify it as a Bronsted-Lowry acid. That wouldn't be totally wrong. Could you classify it as a Lewis acid or base? Well, it's not electron deficient. Okay, you can't put a partial positive charge on nitrogen. It has 8 valence electrons around it, but could it be a Lewis base? So what does a Lewis base do? It's an electron pair donor. Yeah, it could. Anything with a lone pair of electrons can be a Lewis base. So ammonia can be either a Bronsted-Lowry base or a Lewis base. Okay, so just a nice visual to remind you that all Bronsted-Lowry acids and bases are also Lewis acids and bases. How do you identify a Lewis base? Now, we've talked that a Lewis base has to have at least one electron pair of electrons. So it's going to be really important when we start writing out Lewis acid-base reactions that you are able to draw Lewis structures. So you probably learned that at some point in the past, but you may have gotten really rusty. So I'm going to do a simple one for you, and then I would like you to turn off the video and practice going over these again. I do have some other lectures just on drawing Lewis dot structures if you need more instruction. But basically the first step when you're drawing a Lewis structure is count total number of valence electrons. So let's just do a really simple one. Let's take water. And so we know that each hydrogen has 1 valence electrons and oxygen has 6 valence electrons. So we're dealing with a total of 8 valence electrons. So when we're drawing our Lewis structure, we have to place all 8 of those electrons. So you start out by drawing single bonds between the central atom and all the other atoms. And how many electrons have we used so far? Well, there are 2 in each single bond. We've used 4. And so we can't put any more electrons on the hydrogens because they only hold a total of 2 electrons. So our remaining 4 electrons have to go on the central oxygen atom as lone pair of electrons. So that is the Lewis structure for water, and that tells us that the oxygen does in fact have lone pairs of electrons, and therefore this water can act as a Lewis base. So that's what you're going to have to do with every structure to decide whether or not it can be a Lewis base. You're going to have to write out the Lewis structure and see if there are lone pairs on the electronegative atom. So take a minute and draw the Lewis structures of the remaining ones up here and start getting familiar with that. So real quickly, I'll draw them here for you. I won't go through the steps, but most neutral nitrogen containing compounds have 1 lone pair of electron on the nitrogen if there's not a charge involved. And so this would be the same. Now, OH minus, you got to be a little bit careful. Let's kind of take a minute on that. Oxygen has 6 valence. Hydrogen has 1. But then the negative charge tells us we have 1 extra electron. So I have to add that on. So I still have 8 valence electrons just for the OH. So what does that Lewis dot structure look like? Well, let's draw a single bond between the oxygen and the hydrogen. I know that I can't put any more electrons around that hydrogen. And I've used 2 electrons, so I have 6 more electrons. So I've got to put them all around this oxygen. Okay, so the hydroxide ion is actually a better Lewis base than water because it has 3 lone pairs of electrons to serve as a Lewis base. So as a summary, if you're trying to identify Lewis base, you need to have a lone pair available to make the bond with the electron-deficient atom. Most electronegative atoms have lone pairs. So, things like oxygen, nitrogen, fluorine, etc. have 1 or more lone pairs. Now, the electronegative atoms like this, electronegativity definition means an attraction for electrons. So these guys have lone pairs, but they also like to hang on to their electrons. All right, so hopefully you can identify a Lewis acid or base now. What if I gave you a variety of Lewis acids and said which one is the strongest Lewis acid? Or I gave you Lewis bases and said which one is the strongest Lewis base? How would you decide that? Now this is a little trickier, so this is going to require some focus and concentration in case you want to go take a break and come back. So here we go. All right, so here's a typical example. Let's compare ammonia to water. Which one is more acidic? How do I even go about that? Well, it turns out, decide which one's more acidic, you would want to look at the product. If it acted as an acidic compound, in other words, if it donated a hydrogen atom, what would you form? Okay? So if this gave away one of its hydrogen atoms, now remember it's just the hydrogen ion, that it gave away. So if we take away H+, we're left behind with these two electrons and a negative charge. Okay, well, that's supposed to be a negative charge and a hydrogen ion. If water were to serve as an acid, in other words, give away, we would be left with an extra lone pair of electrons, a negative charge, and then the hydrogen ion. So you have to draw the product of what it would make, and then you have to ask yourself, which one of these products is more stable? Because if the product isn't stable, where it came from is like, I'm not going to make you, you're not stable. Remember, nature always tends to go to a lower energy or more stable state. So it's not really going to want to react unless it goes to something very stable. So let's evaluate the stability of the two potential products. All right, so here they are again in a little bit prettier form. And so let's see, how do we decide which one's more stable? Well, basically, which one of these substances can accommodate a negative charge? Which one of these wants a negative charge more than the other? There's one of them that's much more happy with a negative charge than the other one. And hopefully you can remember that the more electronegative an atom is, the more strongly, the higher the attraction or stronger the attraction for a negative charge, more electrons in negative charge, okay? So which one of these is more electronegative? Is it nitrogen or oxygen? Well, you may remember the electronegativity trend on the periodic table goes kind of like this, where fluorine is the most electronegative. So the closer you get to fluorine, the more electronegative the atom is. And so oxygen is more electronegative than nitrogen. And that looks like energetic. I meant electronegative, right? Than nitrogen. And so oxygen can accommodate this negative charge better. So this is more stable. I don't know why I keep switching. Okay. So the hydroxide is a more stable anion than the nitrogen. And so what that means is that water is more acidic and the ammonia is less acidic, just because the product of water being acidic is more stable. Now let's try the same type of thing to see which of these two is more basic. So I challenge you, even if you feel really uncomfortable, try to go through it yourself. I always say this, I know I must sound like a broken record, but you will remember, just like if something traumatic happens in your personal life, you remember it forever. It turns out that when you struggle, even if you make a mistake and get it totally wrong, as long as you then spend the time to figure out why you got it wrong and what you did wrong, you're going to remember it more, okay? So it really benefits you to turn the video off and struggle through this on your own. All right, so what does a base do? Which is more basic? First you ask yourself, what does a base do? I'm talking in terms of Bronsted-Lowry, because I can wrap my head around that better. So a base accepts a hydrogen atom, right? Hydrogen ion. I'm sorry, I keep saying atom. And so let's draw potential products of both of these. If they did act as a base, if they did accept a hydrogen ion, what would they make? Well, we would have one more hydrogen bond, and the lone pair would be gone. It's used to make the new bond. Okay, so we would get the ammonium ion, and over here, we would get the hydronium ion. Okay, and then we do the same thing. You ask yourself, which of the products is more stable? I have horrible handwriting, don't I? Which of these is more stable? So now it's kind of the opposite. because you're not dealing with a negative charge. You're saying which one of these atoms, nitrogen or oxygen, can best accommodate a positive charge. So that would be the one that is less electronegative, right? Because if it's electronegative, it wants a negative charge. It's telling that positive charge, get away from me. I am electronegative. I want a negative charge. So which one of these two is less electronegative and can handle the positive charge better? Nitrogen. Okay, so this is more stable than the hydronium ion, which means what it came from is more basic. In other words, more likely. When I say it's more basic, it's more likely to react as a base. Okay, so again, their picture's a little bit more easy to read than mine. Just a little food for thought. Do you think if you had a compound with an ammonium group, so ammonium, if it ends in IUM, that's nitrogen with a positive charge. Do you think that would be basic? I hope you said no. Because thinking of either definition, for a Bronsted-Lowry base, you would need to accept a hydrogen ion, right? Could that bugger accept another hydrogen ion to be NH5 with a +2 charge? No, that's like a monster. No, if it already has a positive charge, just an easy way for you to remember, if it already has a positive charge, it really is not going to want to take on an additional positive charge. Even if you think of it as a Lewis base, remember that Lewis base has to have a lone pair of electrons, but the ammonium ion doesn't have any lone pair of electrons left. So, absolutely not. So, let's think about a couple of other things. What about CH4? Could that be an acid or a base? Well, let's say it has hydrogen atoms. Could those be donated? Could those be acidic? Hopefully you remember that in order for a hydrogen to be acidic, in other words, to be released as a hydrogen ion, it should be attached to an electronegative atom. Carbon is not electronegative. If you forced it, if you put an incredibly strong base in there, like really, really, really strong, you could probably force that to give away one of those hydrogens, and what you would end up with is CH3 with a lone pair that it didn't have to begin with and a negative charge. But it would not be very happy like that, okay? Carbon is not electronegative. It wouldn't be good at accommodating that negative charge. So could CH4, that's natural gas methane, by the way, act as a base? So could it accept a hydrogen ion? Nah. That's easier. You need a lone pair to serve as a base, either as a Bronsted-Lowry base or a Lewis base, so there's no way. So as you can see, I'm trying to get you really familiar with being able to identify, because some reactions are really obvious that they're acid-base reactions because you're used to the acids like hydrochloric acid, sulfuric, but some of them aren't going to be familiar, and you've got to go through some of this rationale to get to them. All right, so we consider, and we're going to do more of the arrow pushing, curved arrow pushing, we consider the base with its lone pair of electrons to be the initiator of the reaction. So remember I said these arrows go from the electron-rich site, and that's always the base with its lone pair of electrons. So your curved arrow is pretty much always going to start at the base at its lone pair, and then it's going to go and point to where a new bond is being made, and that's at the electron-deficient site on the acid. So let's look at some of them. We have a reaction between ammonia. I think I said this before, but in case not. So neutral nitrogen containing compounds are almost always bases. Now they're weak bases, but you probably know like a solution of ammonia is a good cleaner. So yeah, they're basic. If you put ammonia gas into water, you will get a little bit of the acid-base products from that, and from NH3 acting as a base and accepting a hydrogen ion from water. And then you'd end up with a little bit of hydroxide base in there. So, but another way to just look at it structurally, okay, like if we do the Lewis dot structures for NH3 and water, and what if I asked you, show me the intermolecular forces, the strongest one, the most important one between water and ammonia? This is what you would show, okay? Remember the dotted line means intermolecular force. And remember what I said in the very beginning of this lecture, that when you have a strong intermolecular force, like you have with hydrogen bonding, what happens is this electron-rich species is kind of pulling on the hydrogen ion. It's pull, pull, pull. And by doing that, it is weakening the existing hydrogen bond with, in this case, oxygen. And so when it weakens this bond enough, it'll actually break. And that's when you get the products from the acid-base reaction. So now we've looked at the intermolecular forces, and now let's put arrows in place of those dotted lines for the intermolecular force. The arrow is always going to start at the lone pair of electrons, and it's going to go to where the bond is being made. We are making the nitrogen-hydrogen bond, and so it's going to point to the hydrogen atom. You have to be very precise where the point of your arrow ends up. It should end up right where that bond is being made. And then these two electrons in this bond, which were originally used to make a bond between oxygen and hydrogen, are going to be left behind on the oxygen atom. Okay, so here are your products again, but that's showing with the electron flow. So we've been talking quite a bit about Lewis bases because they're considered the initiator of the reaction. But let's talk about Lewis acids. A Lewis acid, by definition, is something that's electron deficient. Okay, remember that all Bronsted-Lowry acids are also Lewis acids. Okay, so in this reaction, water is serving as an acid. It's serving as a Bronsted-Lowry acid. You know that, right? Because it's giving up a hydrogen ion, which means it's automatically a Lewis acid. So if I were to ask you, what is the electron-deficient site on a water molecule? What site could serve as a Lewis acid? It would be the hydrogen ion right here. So let's talk about some other possible Lewis acids. Maybe some Lewis acids that don't have a hydrogen ion but are electron deficient. So as I said before, the easiest ones are ones with an incomplete octet. Boron you'll usually see with only 6 valence electrons. Aluminum, again, is another one. And both of those are very common Lewis acids. You'll see those quite a bit. And if we were to draw an orbital diagram of boron trifluoride, I meant fluoride here, whatever. It does have an empty orbital, so even though it doesn't have valence electrons, it has an empty available orbital that can hold extra electrons, which makes it a really good Lewis acid. Now, anytime you have a cation, so let's say we had copper +2, that would be a really good Lewis acid. Anything with a positive charge, a full-out positive charge, makes a good Lewis acid. And sometimes simply something with a partial positive charge will be a good enough Lewis acid. So this just is kind of a cool picture. One thing that's a little bit odd with some Lewis acid-base reactions is you get, sometimes you make a completely new bond between the Lewis base and the Lewis acid, and it just stays like that. And sometimes that bond is like transitory and it'll break again. So we'll do more examples later on. All right, so here's an example of, you can classify this as a Bronsted-Lowry acid base or as a Lewis acid base. So let's just talk about it as a Lewis acid base, because just what I said, sometimes the new bond stays and sometimes it creates a different bond breaking. So again, this is ammonia. Start with our electron pair, and our arrow points to where the new bond is being made, and that new bond's being made between nitrogen and hydrogen. But then rather than the whole thing staying together in one big complex, what happens then, all right, is that the bond next to the one that was made breaks. The two electrons in the bond next to the one that was made breaks and goes on to the electronegative atom. Okay, so that's what happened in this case. All right, so a few more examples, and later on the semester we're going to be using more and more of these curved arrows to explain to the reader what's going on in a chemical reaction. And so some of the vocabulary words we'll use are nucleophile and electrophile. So a nucleophile is something that's electron rich, and that'll always be where the curved arrow starts. Okay, an electrophile is something that is electron deficient. Okay, and so it will receive the pointy end of the arrow. Okay, it'll be receiving electrons from another nucleophile. So here's a really obvious one. If you have something with a negative charge and something else with a positive charge, it's really obvious that the thing with a negative charge is the Lewis base. It's got the lone pair of electrons. And the positively charged substance is a Lewis acid or electrophile. And so you just make a bond between the two. Here's another example. Okay, this isn't so obvious. There aren't charges. But you have a lone pair of electrons on the nitrogen, and there's not one on the boron. So this has to be Lewis base. Hopefully you've gotten it drilled in your head now that because boron only has 6 valence electrons, it's a good Lewis acid. And so we make a new bond between the two, the Lewis acid and base, and no other bond's broken. We just made a bond. So this is a big complex here. All right, the final example is one where we make and break a bond. So we look for the Lewis base with the lone pairs of electrons. This one's a little odd, you guys. So this is what, if you take organic chemistry, you're going to see a lot of this. So this may not be really obvious to you. Like, why is this carbon electron deficient? Why is it a Lewis acid? It turns out that any atom that is attached to a very electronegative atom. So we all know, hopefully, that chlorine is electronegative. And so what does that mean? That means that this chlorine is sucking away electron density from the carbon. And so if you were to draw partial charges, you would put the partial negative on the chlorine and the partial positive on the carbon. So that carbon is a little electron deficient, so it can be like a Lewis acid. But now look, we made the new bond here between the Lewis base and acid, but we also broke a bond. So the electronegative atom, the original bond that hooked onto that, those two electrons in that bond leave with the electronegative atom. So you might feel a little overwhelmed. Don't. We're going to keep it real simple. So this is really just kind of an introduction to acid-base reactions using curved arrows, etc. That is it for this lecture.